Hi folks, this is Heath. New week, let's start chapter 15.6. This is a section on triple integrals. We will be spending 2 days on this section. So if you still have questions about this, let me know. We can incorporate some of your questions into Wednesday's video. So we'll spend 2 days on this video. Let me also mention, it seems soon because we just got through the first test, but test 2 will be on Monday, October 19th. So that's 2 weeks from now. We have 3 more sections to cover. We'll spend 2 days on this section. 1 day we'll be spending Friday on cylindrical coordinates. We'll spend the following Monday on spherical coordinates. Wednesday of the next week is going to be a review session, and Friday of next week is a fall break, so we won't have a class that Friday, and then the test will be Monday when we get back. So we have 4 more days of material before the test, and a review session and a day off. All right, so let's go ahead and get started. When we talk about the triple integral of a function over a region, that's denoted by an integral of a function of 3 variables with some sort of differentiation of volume. So like dz dy dx, or dx dy dz, or dy dz dx, or something that integrates all 3 axes in some order. Fubini's theorem applies in 3 dimensions as well. We can set up any integral in any order. Mathematically, that's always possible. Pragmatically, sometimes some directions are harder than others, and so we don't want to rely on Fubini's theorem automatically, but we want to rely on it judiciously, if that makes any sense. If the limits are constants, then we can just change the order of integration freely. If the limits are not constants, then we have to reset up the boundaries, but we can do that. Okay? So let's try a couple of examples. Our first example is just to integrate this function over this rectangular box. Some of you had some trouble with this notation on the last WebAssign assignment. So I want to talk about this notation for a moment. You've seen this notation before. This is just a notation that says that x is between 0 and 1. And this x is not a cross product. This is just a product. Cross product only applies to vectors, and these aren't vectors. This is just an x that changes from one coordinate to another coordinate. If you've seen people talk of like an 8x10 picture frame, the x here isn't a product. It's separating the horizontal dimensions of the picture frame from the vertical dimensions of the picture frame. It's just 8x10. It's that kind of x. And so that we're separating the x direction from the y direction from the z direction. You might also see like a 2x4 piece of lumber. The x is not a product here. It's just separating the length and the width in this case, or the thickness and the depth, however you want to say that. Usually then there's a length to the lumber on top of that. So, but the x is just separating a horizontal component from a vertical component. And that's all that's going on here. This is not a cross product. It's not anything else in that. The x's are just separating directions. So 0 to 1 in the x direction, -1 to 2 in the y direction, 0 to 3 in the z direction. Okay? All right, so let's go ahead and do that. We have to choose an order of integration. And the order doesn't really matter, but let's just go ahead and do dx, dy, dz. X then goes from 0 to 1. Remember, we match up the variables outside to inside, not left to right. So this X goes with the inside coordinates, Y goes with these coordinates, and Z goes with these coordinates. Okay? And then we evaluate these integrals one at a time, starting with the one on the inside. So the integral from 0 to 1, x, y, z squared, dx, is the integral of x is x squared over 2 yz squared, as x goes from 0 to 1. And so that will be 1/2 yz squared minus 0 yz squared, or just 1/2 yz squared. Then we take this answer and substitute that into the next integral. -1 to 2 of 1/2 yz squared dy is 1/2 y squared over 2 z squared, going from -1 to 2 for the y coordinate. So that's 1/2 times 4 over 2 times z squared minus 1/2 times 1 over 2 times z squared. When I plug in -1 squared, I get +1. So this is 1/2 times 2. That cancels. This is z squared minus 1/4 z squared, or 3/4 z squared. And then we substitute that into the last integral. The integral from 0 to 3 of 3/4 z squared dz is 3/4 times z to the third over 3. Plug in 3 and 0. And so we get 3/4 times 27 over 3 minus 3/4 times 0. The 3's cancel here, and we end up with 27/4. Okay? So that's our answer. And let's move on to a harder question. This next question is going to be trickier because it's not already set up for us. That this problem gave us bounds for all three variables. The next one, we're going to have to do some setting up. Okay? We want to evaluate the integral of the function z dv over this tetrahedron that's bounded by the planes x equals 0, y equals 0, and z equals 0. In other words, it's limited to just the first octant, and the plane x plus y plus z equals 1. Okay? So we choose an order of integration. And again, because this region is symmetric, I don't think it's going to make a difference which order we choose. So I'm going to choose dx, dy, dz. Okay. So now we set up the outer boundaries. So the boundaries for dz these are constants. They just are the largest and smallest z value that appear anywhere on this tetrahedron. The smallest z value is 0. The largest z value is right here on the top of the tetrahedron, but it's on the z-axis. So x and y are 0, so x 0 plus 0 plus z equals 1. This is the point 0, 0, 1. And so the largest z value is 1. Okay? So now we have to do something new. Let's talk about the middle boundaries. All right. So the middle variable is y, and so we're moving in the y direction. But x is still unknown. So instead of just like a single arrow moving in the y direction, we're going to imagine a line that has all possible x coordinates at a particular y value. Okay, way of thinking about this is, imagine that the tetrahedron was made out of something soft, like made out of cheese. Okay, and you had a wire, and you were using that wire to push through the cheese and slice through the cheese. So the wire moves in the y direction, but the wire itself goes in the x direction. So the wire that slices through the cheese goes in the direction of the variable that we haven't gotten to yet, the dx direction. But it's slicing in the y direction. So I've got this wire in the x direction that I'm pushing in the y direction, and it's going to slice through this shape. And it enters the shape back here along this wall. Okay? And so it enters a shape where y is equal to 0. And as it slices through the shape, and here's sort of the shape of the slice it makes, the very last place it makes contact with the shape, when it finally leaves the shape, it's going to be somewhere along this line right here. Does everybody see that? As I'm pushing this wire through in the y direction to slice through the cheese, depending on the height I place the wire, it's going to end up leaving the cheese somewhere along this line right here. And so I need an equation for that line. So this line connects 0, 0, 1 to 0, 1, 0. Okay? And because the x coordinate is 0 along this line, then I just have to really worry about the equation that goes from z equals 1 to y equals 1, or z equals 1, y equals 0 to y equals 1, z equals 0. And how would we find that equation? Well, the slope is the change in z over the change in y. So the change in z is -1, and the change in y is +1. And so z is equal to -y plus a constant, and then we can test for whatever constant we get here. In this case, y is 0, so z is equal to -0 plus 1, and then we can check that that works here. Z is equal to -y plus 1, and that gives me 0. Except that I need to express this in terms of y, so I'm going to rearrange this into y is equal to 1 minus z. And that's the upper limit here, 1 minus z. It's the coordinate of the line at which this wire leaves the shape. It's okay to have a z in the expression because z is going to be integrated later. It is not okay to have an x in it because x has already been integrated by the time we get to this point. And so the middle boundaries, 0 to 1 minus z, and I still don't know what these are. These are constants or functions including z but not x. Okay? That is, a variable to the right is okay, but a variable to the left is not okay. And now we have to set up the inner boundaries. And this is like what we did in this case of finding double integrals. We just create an arrow that moves through the shape in the x direction. I'm going to redraw this. And I'll even use a different color for my arrow. If I draw an arrow moving in the x direction, it's going to enter the shape somewhere along this wall back here. And that's where x is equal to 0. And then it's going to leave the shape somewhere along this triangle. It's going to leave along that triangle, and that's this triangle right here. And so I have to write that in order to solve for x. Well, x is equal to 1 minus y minus z. And so we integrate from 0 to 1, 0 to 1 minus z, 0 to 1 minus y minus z, z dx, dy, dz. Okay? Well, we still have to evaluate this, and I have not left a lot of room to do this. So I'm going to do some, be a little creative here. When I integrate this from z, when I integrate z with respect to x, I get z times x evaluated from 0 to 1 minus y minus z. And so that's going to be z times 1 minus y minus z. It's going to be z minus zy minus z squared. And that's what we're going to get for our first integral. When we integrate that with respect to y, z becomes zy. Negative zy becomes negative zy squared over 2. And z squared becomes z squared y. And we evaluate that from 0 to 1 minus z. And that equals z times 1 minus z is z minus z squared, minus z times y squared over 2. So I have to square this now. So that's going to be z times 1, z times negative 2z is negative 2z squared, and z times z squared is z cubed over 2 minus z squared times 1 minus z. So that's going to be minus z squared times 1 minus z is z squared minus z cubed. Okay? So I'm plugging in 1 minus z into all of this. When I plug in 0, I get 0. All right. So what we end up with is z minus z over 2. So that's 1/2 z minus z squared minus a negative 2z over 2, z squared over 2 is minus z squared plus z squared. But then there's a minus z squared here. So that's minus z squared. And then we have negative z cubed over 2 minus a negative z cubed is plus z cubed over 2. And finally, we still have to integrate that from 0 to 1. And so I'm going to squeeze in some room way up here because it's the last place where I can find some blank room. And the integral of this is going to be 1/2 z squared over 2, or 1/4 z squared. The integral of minus z squared is minus z cubed over 3. And the integral of z cubed over 2 is z to the 4th over 8. From 0 to 1, so this is going to be 1/4. minus 1 cubed, 1/3 plus 1/8. And that's, what is it, 3/8 minus 1/3 is 1/24. Okay? So the important part, the takeaway from this, is how do we set up this triple integral? The outer boundaries are constants. The inner boundary, the middle boundary, involves x and y. It's a wire in the x direction that's pushing through the shape in the y direction. And we're recording where that wire enters and leaves the shape. And then the inner boundary only involves the x-coordinate. It's just an arrow moving in the x direction. And where does it enter and leave the shape? Okay? So it's that middle step that's new, that we want to do some practice with. Okay? All right, so let's get some more practice. For example 3, let's evaluate this triple integral here. D is the region bounded by these two surfaces. X squared plus 3y squared is the lower surface. It's a paraboloid that opens up. Z equals x squared plus 3y squared. And then this is a paraboloid that opens downwards. This is 8 minus x squared minus y squared. They kind of meet in the middle. And we have these two paraboloids that are coming down onto each other. Okay? All right. There is no integrand here, so it's like integrating a 1. And so we have to choose an order of integration. I think we want z to be on the inside here because these functions are already set up in terms of z. And if we change them around in terms of x or y, we'd end up with square roots. And so let's leave these in terms of z. Okay? Then our other boundaries here are x and y, and I don't know if it makes a difference which one of those we do first. So we'll do dx, dy. Let's try that. Okay? In order to see the largest and smallest y value, and I know the graph is a little small, it might help if we looked at the intersection. Where do these things cross in the middle? Okay? So where do they cross? Right here in the middle. Okay? So we would get that by setting x squared plus 3y squared equal to 8 minus x squared minus y squared. That's the same as 2x squared plus 4y squared is equal to 8. Bring the x squared and the y squared over to this side. And I'm going to divide by 2 and just get x squared plus 2y squared is equal to 4. If I just look in the x and the y directions, the intercepts for x are x squared equals 4. That will be at 2 and negative 2. But the intercepts for y, 2y squared equals 4 is y squared equals 2. That's square root of 2 and negative square root of 2. And so we have an ellipse like so. And the boundaries for y are negative root 2 and positive root 2. Okay? All right, so now we're going to set up our middle term here. And let's think about how this wire is going to move. The wire itself is going to go in the z direction, and then the wire will move in the x direction. So both of these variables are involved in setting up this middle ground. We create a wire that extends along the z direction. We push it through the shape in the x direction and see where it enters. Well, it's going to enter along the back of this shape. So along the back, it's got to enter somewhere along this curve, and then it's going to push through the shape and leave along the front, which is going to be somewhere along this curve. But we know what this curve is. This is x squared is equal to 4 minus 2y squared. And so x is going to be plus or minus the square root of 4 minus 2y squared. So the inside boundary is going to be the negative square root of 4 minus 2y squared. And the upper boundary is going to be the positive square root of 4 minus 2y squared. And that doesn't look pretty, but I'm hoping that it's going to work out kind of nicely in a moment. Now the inner boundary is just the z-coordinate. Where do we enter and leave the shape as we move in the z direction? We enter it along this bottom paraboloid, which is the one that opens upwards, x squared plus 3y squared. And we leave it along the paraboloid that opens downwards, 8 minus x squared minus y squared. And again, we're still integrating a function that's just equal to 1. All right, this is our setup for this shape. Okay, and so we work out the first integral, the integral of 1 dz from x squared plus 3y squared to 8 minus x squared minus y squared. The integral of 1 is z between these two limits. And so we get 8 minus x squared minus y squared minus x squared minus 3y squared, which is 8 minus 2x squared minus 4y squared. We now have to integrate that with respect to x. Okay. And at this point, the integration may be a little too hard to work out by hand. Let's see, integrate from negative 4 minus 2y squared to positive square root of 4 minus 2y squared. 8 minus 2x squared minus 4y squared is equal to 8x minus 2x cubed over 3 minus 4y squared x. Plug in negative 4 minus 2y squared, or negative square root of 4 minus 2y squared, and positive 4 minus square root of 2y squared. And so that's equal to 8 times the square root of 4 minus 2y squared minus 2 times 4 minus 2y squared to the 3 halves, square root cubed over 3, minus 4y squared times x, which is the square root of 4 minus y squared, minus all of the stuff when we plug in a negative square root of y squared. So 8 times negative 4 minus 2y squared minus 2 times negative 4 minus 2y squared to the 3 halves over 3 minus 4y squared times negative square root of 4 minus y squared. And when we subtract that, mostly we're subtracting negatives each time. And so we get 16 times the square root of 4 minus 2y squared plus or minus 2 and minus 2 times negative, let's see, Negative, negative is positive. This is negative 2. This is negative times a negative. This is not going to cancel. What am I doing? Oh, minus a negative and a negative. That's 3 negatives. So that's minus 4 times 4 minus 2y squared to the 3 halves over 3. I left off the 2y squareds on these terms. I don't know why. And then this is going to be minus 8y squared times 4 minus 2y squared. And then we finally have to integrate that from negative 2 to 2. And this is going to be a really hard integral to work out because of this is going to require a trig substitution. And this is going to require integration by parts. This is going to be pretty messy at this stage. But the last stage would be to use a computer to work out this integral of 16 times the square root of 4 minus 2y squared minus 4/3 times 4 minus 2y squared to the 3 halves minus 8y squared times the square root of 4 minus 2y squared dy. And like I said, that's a little hard to work out by hand, but what I want to do is spend time setting up these integrals, and we did set this up. Okay? Let's move on to the next example. We have a tetrahedron whose vertices are 0, 0, 0, that's the origin, 1, 1, 0, so that's 1 unit out the x direction, and 1 unit in the y direction, and 0, 0, 1, 0, that's just 1 unit out in the y direction, and then 0, 1, 1, that's 1 unit out in the y direction and 1 unit up in the z direction. So it's this tetrahedron here. And we want to set up a triple integral to find the volume of this tetrahedron in the order dy dz dx and the order dz dy dx. And I'm getting out of order a little bit. If we want to find the volume of the tetrahedron, then what we're going to do is we're going to integrate my function is going to equal 1. That's actually on the slide after this, and I did that out of order. Okay? But let's just focus on setting this up. Okay? So if we set this up in the order dy dz dx, my outer boundary x represents the smallest and largest x coordinates anywhere on this tetrahedron. That's 0 and 1. That's usually not too hard to figure out. Then we have to do something involving both variables here. We're going to have a wire that extends in the y direction. Let me move my pen around so I don't keep hitting the erase button here. Wire is in the y direction, moving in the z direction. So the wire is like so, and we're going to push it up through the cheese until it exits the cheese. So it's going to enter the cheese down here along this triangle down here at the bottom. And down here at the bottom, the z-coordinate is equal to 0. And then as we push it up through the cheese, so this wire is moving up through the cheese, it's going to leave the cheese. The last piece that it's going to leave is going to be along this line right here. Okay, the wire is going to move up and up and up, and it's going to leave when it hits that line. Well, that line goes through this point, which is 0, 1, 1, and this point, which is 1, 1, 0. Y equals 1 is the same in both cases. And so what we need to do is figure out how to set this up in terms of z and x. Well, the line that goes through 0 and 1 and 1 and 0 is, again, it's the equation x equals 1 minus z, or z equals 1 minus x. It's similar to the problem we did before. And so we're going to go up to 1 minus x. It's okay to use this variable, not the ones that we're using to create the wire. The wire is in the y and the z direction. We can use x in the answer. Okay? All right. So let's keep going. In our last step, we're setting up an arrow that just moves in the y direction. So it's going to move in the y direction. And it's going to enter the shape along this triangle. And it's going to leave the shape along this triangle. Now this triangle is pretty easy because everywhere along this triangle, y is equal to 1. But this triangle is going to be a little tricky. If I label these points A and B and C, I want to come up with the equation of the plane that goes through A, B, and C. And coming up with the equation for the plane requires doing some finding a normal vector. So the vector from A to B is 1, 1, 0. The vector from A to C is 0, 1, 1. Their cross product, AB cross AC, is 1 minus 0. 1 minus 0, but change the sign, and 1 minus 0. And so we get x minus y plus z is equal to some constant. Well, if I plug in the origin, I get 0. If I plug in 1, 1, 0, I get 0. If I plug in 0, 1, 1, I get 0. But I have to write what y is equal to, because I'm setting up boundaries for y. So y is equal to x plus z. I just bring the y over to the other side, and I get y equals x plus z. And that's the equation for this plane here. Okay? All right. Well, the problem didn't ask us just to set up the problem in this order. It said to do it in this order as well. So let's start with a blank page. We are using the point 1, 1, 0, 1, 0, 0, 0, 1, 1. And we want to set this integral up in the order dz dy dx. Okay? So again, for the x-coordinate, we just want the largest and smallest x-coordinate anywhere in the region. That's 0 and 1. This time, we want the wire to go along the z direction, but we want it to move in the x direction, or in the y direction. So the wire is going to be going up and down. And as it slices, it's going to move through this shape. So the very first time it enters the shape is going to be along this line down here. That's going to be the first place where the wire enters the shape, where it makes contact. The wire is going to be still moving up and down, pointing up and down. It's going to touch that line, and then it's going to start to slice through the cheese. And it's going to leave along this back piece right here. Where along this back piece, this is y equals 1. But along this line down here, let's talk about those coordinates. The starting point is 0, 0, 0. The bottom point is 1, 1, 0. Z equals 0 in both cases, so the z coordinate doesn't make much difference. But the x coordinates and the y coordinates are changing. And what's the equation of the line that goes from 0, 0 to 1, 1? Well, that's just the line y equals x. And so this is just the line y equals x. All right. So then the next example. We're now moving just into z direction. So these are now just arrows moving into z direction. They're going to enter along the bottom of this shape, and they're going to leave along this shape. They're going to sort of enter down here and then pop out up here. So the shape down at the bottom is z equals 0. This tetrahedron, we already figured that out from before. It was x minus y plus z equals 0. But this time we want to solve it for z. So z is going to equal to y minus x. And that's where it's going to go there. Y minus x. All right. This is not easy. This is why we're going to spend a whole nother day of this on Wednesday. Your job between now and Wednesday is to start working through some examples from 15.6. Use your book, pick out some of the problems, work through some of them. If you find some that are difficult to visualize, let me know which ones you'd like me to work through. I'll take some requests tomorrow and put a video together on Wednesday. Okay? So I know this is not an easy section, but I need your help to guide me into what kind of questions to answer on Wednesday. We're going to do one more example. If I want just to find the volume of a three-dimensional object, we have two ways of doing that. We can use a double integral, where we have a length and a width in the dy dx, and then a formula representing the height, and that gives me a volume. Or we can use a triple integral, where length, width, and height are in the bounds of the integral, and then there's nothing else to multiply by, so we multiply by 1. Both of these ways calculate volume. Okay? But if we want to calculate the mass of a three-dimensional object, then I not only need the length and the width and the height, I also need a density. And so if I want to calculate the mass of a three-dimensional object, then the density goes in the center times length, width, and height. It'll be a triple integral. The limits of integration represent the boundaries in all directions, and then a function that's being integrated represents density. We're going to set up a mass example, and then we're going to wrap up. Okay? So here's our mass example. We want to find the mass of the solid whose density is 2 and is bounded below by the disk x squared plus y squared is less than or equal to 4 in the xy plane. So let's talk about that. If x squared plus y squared was equal to 4, that would be a circle of radius 2. But since it's x squared plus y squared is lesser than or equal to 4, then it's the entire disk inside here. And it's bounded above by the paraboloid 4 minus x squared minus y squared. So that's, I didn't draw this very well, but that starts at 4 and then opens downwards. It's a paraboloid opening downwards. And so it opens down, the paraboloid continues on forever, but we are bounding it below by this disk. And so we want to find the mass of this bump-shaped region here. All right. In the interest of time, I think we're just going to set this up. The function we're integrating is the density. And we choose an order of integration. The smallest and largest x coordinates are back here and right here. That's -2 and +2. All right. The wire that we use to slice through this shape is pointing in the z direction, but it's slicing in the y direction. So the wire goes up and down, but it moves in the y direction. And it will first contact the shape somewhere along this boundary. Depending on where we position the wire, we could position it way up here and it'll contact at this point. We position the wire back here, it's going to contact at this point. If we position the wire right on the axis, it's going to contact at this point. But depending on where we position the wire, it's going to contact at one of these points. And that's along this circle. So y is going to be equal to this negative square root of 4 minus x squared. And then it'll leave along this front circle. Positive square root of 4 minus x squared. So the wire, we have a range of places where we can start the wire, but it's going to move until it hits. And this circle at the base is going to be the first place where that wire starts to slice. Then to set up the inner boundaries, now we're just creating an arrow that's moving in the z direction. It's going to enter the shape along this base. And along the base, z is equal to 0. But it's going to leave the shape along this curved surface. And along that shape, z is equal to this expression here. 4 minus x squared minus y squared. Okay? All right. Hold tight on this section. We're going to spend another day of this on Wednesday. And again, let me know if you have any questions about what we did today. Thanks for coming.